Welcome to another one of my Leetcode videos. In this one, we'll be solving this Google interview question 1146 snapshot array. So basically, the problem says that we are going to implement this class called snapshot array, which is initialized with a length. And the user can set a value for a given index and they can get the value. But there's also this concept of snapping where if the user calls snap, it takes the snapshot of the current array, and then the get is based on a snap ID. So for example, if I instantiate snapshot array, set the index 0 to 5 and then take a snapshot, it returns me a snapshot ID, which is here, total number of times we call snap -1. So it will return like 0 as the snapshot ID, which is here. And then if we change the index 0 to 6, when we get this, if we get the snapshot at 0, we return 5. So because it's the value at that snapshot. And so the first option to solve this problem is just we just maintain an array of size length, and then every time we call snap, we kind of save this entire array in a list, and this list is a list of int arrays. And then when get is called, we just look up the list, add snap ID, and then index, right? So we look up the list that we stored for the provided snap ID, and then in that int array we look up the index. So this is kind of the naive or brute force solution. But the problem with this, so if we analyze the space and time complexity, so the time complexity for every one will be O1 because we're just like inserting or retrieving. However, the space complexity here is going to be O of the number of snaps times length, right? So the more we call snap, we just keep taking copies of the array, and this could be inefficient. And the crux of this problem is to optimize the space, because you'll notice that if you use the naive solution, it'll give you a memory limit exceeded. So the question is, how can we optimize the space? Well, one way to optimize the space is, instead of saving an array of size length, we could change this to a map, right? So we change it to a map of index to value. And now, if we have indexes that are not set, then we won't have unnecessary values. Then here, instead of being a list of int arrays, it can be a list of map index values. So every time we take a snapshot, we kind of store it in this list for the snap ID. And then whenever we do a get call, we look up that specific snap ID and then get the index in that map. However, this is also not optimum because it still is a function of the number of snaps. If we keep snapping with the same array, it'll just keep copying this map every time. And so what we can do instead, option 3, is we kind of combine both of the approaches. So basically we keep a map of element. So basically it will be index. So the key will be index and the value will be snap ID to value. So this says for each index, here are the snap IDs that change the value. So that way we only store an entry if the value actually changes. So it will be an order of how many times set is called. instead of creating copies. So this, we avoid creating copies, but what that means is when we do a get, we have to look up the closest snap ID because we might not have an exact match, right? So let's say you stored index 0 and set the value to 4, and then we snap and then we snap. But in these two snaps, we did not change the value of index 0. So then this will be snap ID 0. This will be snap ID 1. But when we do a get call with snap ID 1, we should still get the value of 4, right? But in this map, we won't have snap ID 1 because the value of index 0 only changed once, right? So during the get call, what we have to do is look up the closest closest snap ID to the provided ID that the user is looking for. And the way we can do that efficiently is using a binary search. So we will basically do a binary search through this map, and look it up that way. So let's write the code for this. First, we'll have our map of index to snap ID to value, and let's just initialize that over here. And then we need to maintain our current snap ID equals 0, so that we can use this to insert things into this map. So when something is inserted, first we need to make sure that the map exists. So if not dot contains key, then a new hash map in there, and then all we have to do the current snap ID and the value. And then when we snap, all we have to do is cur snap ID plus plus, because we just increment it. Now the interesting thing will be on the get. So this is actually, we have to make it. So let's use a tree map. So at the get, what we need to do is we look up the index, and that will be our tree map. And then we get the, I think it's called the seal entry, the floor entry that's closest to the snap ID. So we basically get the snap ID that's less than equal to this, and then the value of that. So let's try to run this. There's a case where we can get where it doesn't exist. Let's see what the behavior is. Oh, it says initially each element equals 0. Okay, so it could be that we saw this at a later point, so we need to check that too. Yeah, so I've rewritten this code with optional, and what this will do is if any of these are null, it will just jump to the or else and return 0. So let's see how that does. Cool. So yeah, the solution was accepted. Thanks for watching. I'll see you in the next one.